Well, in the short term, while this thing is loading, I'm going to go ahead and start just sharing from this other screen. So we'll do it this way. Sorry for all this. I tried to be a lot more organized on this. Um, Let me share the other screen because apparently it's going to that one. There we go. Okay. So the first homework problem was 121. So you can see the homework problem, correct?
Yes.
Okay. So the very first problem that I got asked about, and this is kind of a positive sign convention, and uh, part of what makes this class a little difficult to get started on is that in physics class, everything kind of focused on following the electron, which is still true life. I mean, the electron is actually the charge that actually is traveling. Um, However, when we actually, especially in engineering, we actually analyze things from a positive sign convention. So we follow the what I call the whole, basically the positive charge. There is no positive. The proton isn't actually what's moving, but it's just how we think. So we look at the positive terminal, positive current is positive power. And so this kind of initially causes a little bit of a disruption in the way you're thinking, depending on how vested you were in physics 207, 208, or whatever you learned there for electro-optics class. Um, Let me go ahead and just shut off this iPad and recycle it. Hold on. Go. All right, so here we were given three elements, and so they were going to ask in three different parts, element A, B, and C. They're going to give different voltages and different currents, and they're going to ask you to say whether the energy was being absorbed or being supplied, or if you will, generated by the element. So if you have with with an element given with its terminals, plus and minus, good positive, negative terminals. If the current is leaving the positive terminal, meaning that it's coming out of the terminal like this, leaving the positive terminal, and the voltage is positive, so that the actual voltage is this is truly the positive voltage. So like we had, let's just pretend for a moment this was 10 volts, positive to negative. Absolutely, the absolute voltage is positive 10 volts here, and the current leaving, let's just say, was a positive 1 amp out of the terminal. This would be a generator because the current is leaving the positive terminal, doing some work, and returning to the negative terminal. Um, if the current was reversed, if the current was going into the positive terminal, then that means that the current, and of course the positive, there's still a positive voltage drop from here to here. So we have current coming in the positive terminal and the voltage is positive. So therefore, that would be a device, an element that would consume energy, like a resistor, for instance, which is what we're studying right now, or a motor. Um, we're going to get into inductors and capacitors here in just a few weeks. Those actually have both properties. They both supply and consume. But generally speaking, a lot of the devices we look at, they consume power. So devices like a battery, a power supply, things like that produce power. So they're going to give you these using sign conventions. They're going to give you the voltage values. And obviously, the value of the voltage could be positive or negative. And the same thing with the current. The current, based upon the listed terminals and or arrows defining the analysis direction, if you will, could be positive, negative. That just, for instance, if IA was given here, which in this case it was 3 amps, actually was listed as minus 3 amps. That means that the current given the direction of the arrow means we're analyzing it for current going this way, but in all actuality the current was traveling the opposite way, so hence it would be negative. That's what's happening. So in this case here we're given VA as, let me get a little pointer here. We are given VA as minus 14 volts. So that means from this terminal, with this being the reference point, where we're, if we had a voltmeter, we would put the black end, the black wire right here. That would be our reference, and we're measuring to the positive terminal. So we're measuring from here to here, and that reading was minus 14 volts, which means technically the power, whatever this is backwards. It's actually hot, 14 volts here and 0 volts here. So from a reference point of view, there's more negative potential here. So it's minus 14 volts, and we've got 3 amps coming out. So since the equations, we have here are the terminology we have matches our equation. We have VA and IA. Power is equal to voltage times current. So we take voltage times current, and that equation is defined as positive terminal with the current leaving the positive terminal, like this. So the equation P equals V times I follows this, if you will, nomenclature, this sign convention that we have here in this drawing, analysis direction, if you will. So we have minus 14 times 3, and we end up with minus 42 watts. So minus 42 watts tells us what? Anybody?
Energy is being supplied.
Energy is being supplied because it is negative. Um, So we end up with minus 14 volts, minus 3 amps, and we end up, well, I said, well, no, IA, so I might have this wrong here in my notes. It is IA, oh, that's right, excuse me. IA is reversed, yeah, duh. I'm still thinking like a resistor. It's going the other way. My still not enough coffee yet, I guess. IA is leaving the positive terminal. Actually, it's supposed to be going in for the P is equal to I times A. So we end up with positive to negative, it's minus 3 amps. So it is 42 watts total, minus 14 times a minus 3. And it's, again, the reason for that is simply because the current for the, I'm trying to get this thing up so I can actually draw on the screen here. So you're going to have to deal with me using a mouse to draw here. So P is equal to V times I, but this equation is based upon a current going this way, down from positive to negative. And so because the current was given as IA here going this direction, that means that the actual sign from positive to negative was minus 3. The voltage stayed the same because it was given to us as a positive to negative value, VA to VB. And so hence this ends up just being 42 watts. Is there anybody have any questions on that? All right. And because of that, the power is being absorbed here. So it would be generated if it was the other way around. So sorry for the confusion initially. I was brain locked looking at the thing. So I'm trying to do two things at once here. Let's see. I'm scrolling down actually to this recitation that I'm doing right now. Just here, here it is. Okay. So on this problem here, so now we're on B. This here, and I apologize for this convention being shown in the book and in the homework. Um, as I told the class in person the other day, this you know basically arrow-based voltage concept is not very common. I in the industry, I have only seen it once. I've been doing electrical engineering, practicing electrical engineering, in all sorts of different industries, everything from oil and gas to working for NASA, just a little bit of everything as a consultant. One moment I'm doing lift stations for sewer, and the next minute I'm working on something for NASA. The next moment I'm working on some little, you know, horse leg monitoring contraption, and I'm not even kidding. That's an active project actually. So it's a little bit of everything as a consultant. And in that, I've seen all sorts of engineering diagrams dating all the way back to the 1940s. And that was probably the last time someone brought an amplifier in that was built like in the 50s, and they needed it repaired. And the schematics use this nomenclature. So it's not, it's a very old method. It's still around, but again, very rare. And all that this nomenclature is that this is the negative terminal and the arrowhead is the positive. So the arrow start is negative, the arrow positive, arrowhead is positive. That's all it is. And so it's the equivalent of this here. It's just with this being negative and this is being positive. So I know the arrow will throw people off. So here we're told that VB is 10 volts. So again, this is the positive terminal, and this is the negative terminal here. And then IB going from positive to negative is 4 amps, and hence we end up with the same exact equation. Voltage is 10 volts. The current from positive to negative is 4. Power is 40 watts. It is being absorbed. VDE is 20 volts. Here, this nomenclature is using the terminal names, so D and E. And then, of course, for the current, they give it the exact opposite way. So they give D and E. We can label it positive, negative, as same thing as before. But they have the current going from E to D, which means they're labeling the current I, as 4 amps going this way. But again, for our formulas, it is the positive sign convention. So we have, the voltage from D to E, we're going to assume is positive. We just take D as the positive terminal, and as such, it's just 20 volts. But since the current was E to D is 4, then that means from E to D was 4 amps, then D to E would be minus 4 amps from positive to negative, and hence we have minus 80 watts. This one here, the power is being supplied. So what we have here again, the emphasis here is things are in series. And so what we end up with is we need a 5 ohm resistor and a 10 volt independent voltage source. So they already give you that right here. And then you have a 2 amp independent current source. So technically it doesn't matter where these elements are, but they kind of show you, they've already got them oriented in a way. So the only 2 amp current source is basically vertical. And so it would go here. And then they get two different resistors. One would fit right here because it would be vertical. The problem with that one is it's in parallel. It's not in series. So the other element would be this one here. This is why I hate using a mouse because I get these weird drawings. Um, so that we end up with something like this. So any questions on this particular one here? Because I know someone had asked me on this one. So, okay. All right, so moving on. So here was another problem. This was a KCL tutorial, just having you think what's happening with Kirchhoff's current law. Again, Kirchhoff's current law just says if we have a node, then there's no storage or charge in the node. So therefore, um, the current going, is being split. It's either all entering is zero or all leaving is equal to zero. When we write our equations for node analysis, which is what we started to do on Wednesday, I use leaving. It makes the analysis equations easier to set up. Um, but for purposes of this particular problem, we were just being asked to solve for a particular current given other additional currents. So we are given that I1, this one here, is minus 2 amps, since they're kind of also making sure you pay attention to the units of measure. One is given in milliamps, one is given in amps. For the purposes of solving this, I'm going to use amps. So it's just minus 2 amps, and it's leaving this particular node right here. So we have a node. Now for my online students, because I know I hammered this really hard the last couple of lecture days in the live class, one thing to make sure you pay attention to is a node is not a dot. Um, so for everyone who was in class on Wednesday live, I know I'm beating a dead horse. Um, but again, this is not graphical analysis. This is basically just electrical connections. So wherever electrical devices come together, that is a node. Um, So one thing just to keep in mind, because this is going to trip you up on the test if you don't get this particular right. So if I've got a wire, and again, this mouse is doing weird things, and if I have one element here coming off, and pardon for the poor drawing because I'm literally drawing with a mouse. Um, if I have this type of situation here, how many nodes do I have on this drawing? So I want to count up the number of nodes I've created. Anybody?
One.
One node. And again, for anyone who's like, wait, I count three dots. Again, it's not the number of dots, it's the number of actual electrical connections going on. This is all right here. This is all one big wire mess. And this could be wired in all sorts of different ways, and you can see this in the field when you ever inspect an electrical harness. There'll be all sorts of taps coming off it. Again, we're considering a wire as an ideal wire. In fact, everything in this class we consider ideal. We'll model real world things because wire really does have resistance to it, but we will model things accordingly. So this is all one big wire and connecting all this together. So there is just one huge node right here that all this connects together. Very important concept. I know it seems simple at first and like duh. When we write equations for the nodal analysis, that is the number one problem I see on, especially on tests, is I'll end up with people writing, they'll see a circuit like this and they'll write an equation for this node, an equation for this node, and then a separate equation for this node. And technically you can do that, but it's effectively the same equation every time. And so, but they would like, oh, well, I'm going to use this device and this device, but not use this device in the equation for number one. Or just it just ends up this mishmash of weird equations, and they throw that together and then try to solve it, and it completely collapses, and they're confused at what happened. So that's why I point this out. All right, so again, we've got this node here, and we're looking for what is the current, a given current number one and current number two. Well, current number one is minus 2 amps, and its leaving is going this way. And then we have current two, which is the same current because it's going through 5 and it's going through 7, and it's going to end up doing this, and it's all coming together at this node here. Does this. Um, And so that means current 4 is coming splitting. So we could technically say that I1 is equal to 2 amps leaving this way. We've got I1 is minus 2 amps this way. And we have I2 is 1 1/4 amps coming into that node. This is really going to tick me off. And we end up with I4. So basically, we have I2 and 4. I2 is entering, I4 is leaving. All that has to equal to is 0 in the end. So we do completely leaving. We end up with minus 2 plus I4 plus minus I2 because I2 is coming in, so we have to subtract it. So we end up with 1 1/4 and then 2 amps is leaving. So that means we end up with what do we end up with? We end up with 1/4 amp, I think, left over. So we have uh, 0.25 amps has to leave and go this way. Um, from because we have a total 1 1/4 coming in, or excuse me, I mean, so to get 2 amps coming in really like this, excuse me, I'm getting all my, I forgot. Yeah, this is minus 2 amps. So is there a way to type? So we end up with I1 equal to minus 2 amps. We have I2 equal to 1.25 amps. And we end up with all leaving, we would have I1 plus minus I2. So, or well, plus I will do I4 minus I2 equal to 0. So that's our equation. And we can solve I2 is equal to I1 plus I2, which ends up leaving us with, excuse me, I4. I4 is equal to minus 2 amps. So this is going, so I1 was minus 2 amps. Yeah, so minus 2 amps plus I2. Let's see, what do I get? Hold on. Be I2, be I2 minus I1. Got to pay attention to my algebra here. So we end up with I2 is 1.25. Subtracting minus 2 amps. So we end up with, what is that, 3.25 amps. So does this make sense? Ready? All right, then we have something similar here. So for this particular problem, we have, we are given, we're being asked to solve for I7. So we have the same setup. I1 is equal to minus 2 amps. I2 is 1.25 amps. And I7. Well, I7 is equal to I5, which is equal to I2, which is equal to 1.25 amps. This is the same current. All right, 1.62. So we were asked to find IR flowing through the resistor. So we have a current that's here. We take I as 2 amps. So 2 amps is flowing out of the power supply into the 5 ohm resistor. And then it has another power supply on the other side, a voltage supply of 10 volts. So current is 2 amps. It's an ideal current supply. So no matter, regardless of the circuit here, this current, given that this is just a simple series resistive or series circuit, IR by definition is 2 amps. It cannot be anything else but 2 amps because it's an ideal current supply. So it's right there. There's your answer for that one. Find the power of the current source. So that'll be, again, with the terminals being positive, negative, with the basically arrowhead being positive, the arrow tail being negative. We need to try to find the power of this device. So we need to find the voltage drop across this. Well, that voltage drop is going to be the sum, because of Kirchhoff's voltage law. It's going to be the sum of all of the other two voltage drops, because it has to end up balancing out to being zero. So this is 10 volts. We're given that. So the question is just, what is the voltage drop across the 5 ohm resistor? We use Ohm's law, which is just V is equal to R times I, with this being the positive and negative terminals. So with current entering the positive terminal, we end up with V is equal to 5 times 2, or 10 volts. So the voltage drop across the current source would be from here to here, 20 volts. So this being negative and this side being positive. If that's the case, with current leaving the terminal, because the positive sign convention says, P is equal to V times I, with the I going from positive to negative. So now the current is negative, minus 2 amps, times 20 volts, leads us to minus 40 watts. So the current supply is producing or generating 40 watts worth of energy, but using the power sign convention, it's minus 40 watts in the circuit. Any questions on that? Okay. Find the power in a resistor. There's various formulas for that. I squared R, V squared over R, V times I. But we just found that voltage was 10 volts across the resistance. So that's 10 volts times 2, 20 watts. If you use I squared R, that's 4 times 5, 2 squared times 5 ohms. So a variety of ways to get there. So 20 watts. And then find the power for the voltage source. Well, here, even though this is a power supply, and technically, usually power supplies we expect to generate current and push current out its positive terminal. This one here is because this is an ideal current source, it actually is absorbing, it's actually taking current in the positive. This power supply is going to push current into this power supply just by the nature of how these are ideal devices. And as such, we have 2 amps going in the positive terminal. The power equation, P is equal to V times I, is 10 times 2, end up with 20 watts. Here, we are asked to just label things. So I'm gonna just grab one of these here so I can type it. So we're just asked to label stuff. Um, So what, like what is the voltage, what's the current, so on and so forth, given the terminal. So this is just a basically learn your sign conventions. Um, so you have to choose the right units of measure as well. So you had to, I think all of them default to volts, so you have to make sure you choose if it's millivolts, volts. Here they give you units of millivolts. So Vx was minus 2.9 millivolts from terminals 1 and 2. Terminal 1 being the positive terminal, negative terminal 2 being listed as negative terminal here. So this right here would be simply minus 2.9 millivolts. So you would put that and then millivolts here. Um, all right, and then the current for this particular one is going to be in units of milliamps, and then it is going from entering terminal 1. The actual current is zero point 0.9 milliamps coming in terminal 1 and leaving terminal 2, but the arrow for analysis was the opposite direction. So this will minus 0.9 because that's what this would measure. Then we come over here and do this other side, they're just labeling it differently. Here they have the positive terminal in pin 2 and the negative terminal in pin 1. Well, again, the voltage drop from 1 to 2 was minus 2.9, so this is just flipped. Still the units of millivolts. And here, the current, again, is milliamps. And in this case, it is going in at positive into terminal 2 by the analysis, but the current is still, by the terminology, we're told the current is still from pin 1 to 2, so it's still minus 0.9 milliamps. Anybody have any questions by this? All right. We have then here, we're being asked to find the power of this particular system here. And so here, this is going to be in units of milliwatts because we have a milli involved. We have milliamps times volts. So by just nature, this is going to become milliwatts. And so we have 5.8 volts, positive, negative this way. And then we have a current that is minus 0.9 milliamps coming in this terminal. So if this was a positive current, then this would be positive watts, but it's not because it would be this sign convention with the arrow going in positive. So it's going to be a negative power just by the default. So it's going to be 5.8 times 0.9 um, or minus zero point 0.9. So 5.8, 0.9 negative. We end up with minus 5.22 milliwatts. And then over here, we've got the same thing. So it's going to be the exact same value because it's 0.9 and 5 minus 5.8. So let me just copy that. The question is just going to be what is the sign? So here we got minus 5.8 volts with this being positive negative. So the voltage is actually, really it's really more positive over here in reality. So it's a negative voltage, but the current is going from positive to negative. So the current is this time it's basically completely flipped system. So instead of positive voltage with a negative current, We now have a positive current with a negative voltage. So the net result is exactly the same, minus 5.22 milliwatts. Any questions so far? All right, so here we are told to come up with, what is the power in element number 5 given everything. So we're just told we have 5 elements. They tell us that they want to know how much power is dissipated or delivered by element number 5. And all this is just a summation of power. That all power, typical energy stuff, it all must equal zero. It is either going to be completely generated and then dissipated. There isn't any leftover energy. It is completely consumed in the circuit here. So we end up with power total is equal to P1 plus P2, P3 plus P4 plus P5. So that's what we know, and we're told what all of these values are, and we're needing to solve. And of course, PT must, in the end, the total sum of all of this must be equal to zero. So now we can resolve this for P5, which is going to be minus the total sum um, of basically, because we're looking for minus P1, minus P2, so on and so forth. So just minus times uh, P1 plus P2 plus P3 plus P4 plus P5. So the total ends up being, it's going to be what's left over. So here we have 840 milliwatts negative. So we'll start with that. Adding 248, adding 772, and then being delivered 220. So that's negative. You can either sum a negative or just subtract. And we're left with, let's see, make sure I got this, 840, 248, 772, and then 220 subtract. And we're left with, this all together leads us to minus 40 milliwatts. Of course, taking the, sign of that, minus one that, we end up with 40 milliwatts is the leftover power. And if you go back and stick that in, it'll all equal zero. So this problem here was all about just knowing your powers and paying attention to the convention. So kind of the same thing that we had up here. So again, these are questions that students have particularly asked. So the units here are all watts. So I went ahead and left it in watts. So you had to make sure if you did this problem, this is Pearson. So you have to really make sure that you pay attention to before you hit submit, make sure that everything looks correct and really do pay attention to your units of measure. Uh, So in this case, it's watts. So we have this particular element here, positive to negative, is 9.5 volts, but the current is 2.5 amps going from minus to positive. So it's 9.5 times 2.5 negative, and we end up with minus 23.75. So minus 2.5 amps. This one right down here, let me just copy this one. This one here, we have the current is 1.6 amps coming in the negative terminal. So that would be minus 1.6 amps per the terminal nomenclature. So minus 1.6 times, using the nomenclature, positive to negative, minus 4.9. So minus 4.9, multiply those two together, we end up with 7.84 watts. Power 3 over here, we'll do this one next. It's 3.7 times 2.5. because both of them are positive. So 3.7 from positive to negative, and the current is going from positive to negative, and we end up with 9.25 watts. Number 5 is positive to negative 0.9 volts, 0.9 volts, and 1.6 amps going in the positive terminal, and we end up with 1.44 watts. And then P1, we have minus 0.59 amps coming in the positive terminal, but we have a potential of minus 5.8 volts with reference to the positive terminal. So minus 5.8 times negative 0.9 ends with 5.22 watts. All right. Anyone had any questions on this? Um, here, this was just an energy problem. I don't know if someone, I think I might have just left this in here from the homework review. Um, this here just was like you're given this formula: terminals of electrical device are labeled A to B. If the voltage is minus 10 volts, how much energy is exchanged when a charge at 2 coulombs move from device A to B? Again, it's very important to realize it gives you the specific charge. This is not an electron. This is just a charge of 2 coulombs. So the voltage potential is minus 10 volts. The current is again related to time. So current is coulombs over the time, where the time in this case, we're not given time, but we know that the current is positive because it's just 2 coulombs. So, so I is positive. Energy is equal to work, which is just work over a period of time given power. So P of T. So joules, watts is in the units of joules per second. So if we know the time around, we can go back and figure that out. But again, we're being asked find energy. So we have minus 10 volts times 10 coulombs. That's the P part, the V times I. And we know it's positive. So and one thing to note, because I know a couple of people had questions about this, because there was a couple homework problems as well, like dealing with energy. And you're given like currents that are negative, just like in this case, we have current that's positive, but a voltage that's negative. Energy is always positive, so hence the absolute measure sign. Um, a little weird side note, there is some theoretical physics dealing with negative energy, but everything that we do from an engineering perspective, everything that we do in our industries, energy is positive. So that's 20 joules of energy. So, and of course, since this is the power is going to be negative, in other words, it's minus 10 volts with a positive current, then that means that this energy is being taken, it's being supplied by the device. This is a power supply of some kind, because the current is actually leaving um, out the, if you will, negative terminal. That's really more of the positive side. It's like, so the device is it's it's providing power because the power is technically negative. All right. This problem here, I usually do this, and I'll do it again at the homework review, because this one trips up everyone. This problem here tripped me up the first time I ever solved it in the homework 6, 7 years ago. Um, what's complicated about this is not, and by the way, this is not a problem that you would see like on the test. This here is just to make you think. And so the first time I did this problem, what I did is the way I solve any of these equivalent resistance problems is I like push an imaginary current into terminal A, and I go, do I split or do I stay in series? In other words, do I just keep going from element to element? And if I split, that means I'm making some parallel path. In this case, I split into three. And that's and so I redrew the circuit right here in just 2D form instead of 3D form. So basically we got this cube here, but we want to remap it. And so I redrew the circuit. So it splits, and then it splits again, and then it all comes back together. So it goes into 3, into 6 elements, and then back to 3 elements. If you try to solve this for the equivalent resistance, you will hurt your brain. I did. I finally screamed uncle and looked at the solution because I'm like, this is starting to hurt. And the solution kind of surprised me. And I basically, the solution is what I just described. It's the current is split in threes, then split again in half from there. So split into a six and then split again back to a three. And so there's this symmetry thing going on. And so if we kind of look at the circuit into three elements, um, if we inject this current R, we evenly dice. The resistors are all the same. We're just being asked to solve, you know, what the equivalent resistance is. We're told what R is, and it's the same for all of these. We just need to inject current and see what happens. And so whatever that current, arbitrarily set it as I. So we have a third current here, a sixth current, so going through each resistor. So we have a third of the current going through these resistors, 1/6 of this imaginary current is going through these resistors, and a third of the current is going through these resistors. And so we end up with kind of a, from terminal A to B, there's some arbitrary voltage V, and then the voltage drop across this, and this must equal zero, and must all add up to V. If we did an analysis where we put a power supply through here and we did KVL with that, V would have to end up, whatever the power supply would be the three voltage drops across these three different equivalent blocks. And so we solve now for R equivalent. R equivalent would be V divided by I. So if we basically this right here. So we solve for the resistance given V and I. Again, it's arbitrary. I really don't care what V is, and I really don't care what I is. I'm just trying to solve this. So we end up with a third plus a six plus a third, or it ends up being 5R over 6 if you put all this together, which ends up being 16 and 2/3 ohms. Again, this is a little mental, see if you're kind of like how you're thinking. I would personally would not have gotten this. I would have kept banging my head on this. I probably would have done some sort of numerical method and try to solve it, brute force. So when I kind of saw them, as soon as I saw them do this, it's like, oh, this makes a lot more sense. I'm just going to bring this up. I had this in the lecture notes, and we'll be done here in just a minute. Um, just so I could cover it again. I'm pretty certain this was in the online class video lectures, but just to say I did, and because we're really now into nodal voltage analysis. No one asked any particular problems on nodal analysis. I guess no one's gotten to that really yet. It's kind of the newest homework. Um, so it's understandable that no one asked questions on it, but this is really what the next several weeks, really the next pretty much next 5 weeks is all about in this class, is voltage analysis and mesh current analysis. So we're going to be hammering this home, or I'm going to be hammering this home all the time. So what we have here is a circuit, and again we have three nodes that we're solving for: V1, V2, V3. Notice again here, electrically it shows two dots here, but this is just all one node. What makes this particular problem more complicated is we have this little power supply here. And so nodal analysis is all about Kirchhoff's current law. And so we would write equations for each one of these nodes in terms of current. And we use Ohm's law to get current. So the way you do this is because we don't know what the current going to this 15 volt, we're going to have to make it something here in a minute. So the first one's fairly straightforward. We've got the current that's going, from this terminal here through the 2 ohm resistor. So that is this first term here, V1 over 2 ohms. That's literally the current. This is why I do leaving, by the way. So we've got the current leaving this node, V1 over 2. And then we have the current on the left, which would be -1 amp because it's entering, hence why it becomes +1 amp. So normally it's this. If you're writing your equations completely out, it would look like this. So, of course, I just went ahead and simplified it immediately, just doing this. And then we have the current that's going through the 5 ohms, which is the difference, the voltage drop over the 5 ohm resistor from V1 to V2. With this is being positive, again, the current's going from here to here. So V1 minus V2 over 5, all that must be equal to 0, assuming minus 1 amp. So hence we end up with this equation. So that's equation number 1. Equation number 2, we're doing the same thing. We've got the 10 ohm resistor current leaving this node. Then we've got the current that's going through the 5 ohm, which happens to be the exact opposite of this one. Always think, and again, the reason why again I do leaving currents is because the node voltage that we're solving for, that is always positive in the equation. So V2 minus V1 over 5, and it should mirror this one. So these are they are symmetric. Except instead of V1 minus V2, it's now V2 minus V1 over 5. We have the 20 ohms, which is now V2 minus V3 over 20, so this current here. But there is a current that does come off of here. Leaving, it would be minus, and I went ahead and arbitrarily assigned it. I assigned it as going through the power supply from negative to positive. It doesn't matter which direction you choose, you design it, but it has to stay that way. So, either it's going to go from positive to negative or negative to positive. I pick one. I pick, in this case, entering V2 and leaving V3. So again, this would be minus I15 equals 0. Put it on the other side. So the same thing again for node 3, V3 minus V2 over 20. So it's literally this exact term just flipped. And then instead of this being minus I15, it is plus I15 here. So again, just to, minus I15 equals 0, hence where we get the just our algebra, we just flip it over to the other side. And that has to equal 2 amps, because to make this equal to 0, this would be normally minus 2 amps equal to 0. So that's where everything is. So now we have 3 equations. We have 4 unknowns. Because we have 4 unknowns, which means we need one more equation. And so we have to look at everything. It's like, can we get a relationship in our terms for something else? And we do have that. We have that in the fact that we know that voltage number 2 is equal to voltage number 3 plus 15 volts. I mean, it's just by default there because this is power supply here. It's going to raise this voltage up 15 volts and put it right there. So there is a relationship between V2, V3, and a power supply. So now we have 4 equations and 4 unknowns. Now you can go through and solve this algebraically. And I think in my lecture notes I did that. But this is not how I solve that. I instead, do this, and I solve it using linear algebra. We come up with a matrix A. I went ahead, I think I reduced things a little bit because of the relationships, and solve for V1, V2, V3, and we end up with, a set of equations. Now, just to show y'all live for the last little bit, what this looks like. This is MATLAB on a computer. 'Cause I know in class I showed MATLAB on my iPad, which works perfectly fine. Again, especially for all the students that are online, I highly, highly, highly recommend downloading and using MATLAB for this class. It's what I primarily use. It's what I use for the tests. It's what I use for the quizzes. You can use Python. You can use your calculator. I have an HP Prime over here. I have 2 HP Prime, but I'm a HP-aholic. I'm staring at 3 calculators within a foot of each other right now. So my HP Prime can solve this. My HP, I don't know, I don't think the 35 can solve it, but the definitely the Prime can solve this. Because you can literally put the matrix in, and all the matrices is just the coefficients. So um, please review, if you haven't had a chance to review the lecture on this, learn this method, because the test will have equations like 8 node equations. So you're solving a linear system of equations with 8 unknowns, which is By hand, I don't even think about the math on that. If you do it on a computer, man, it's easy. Again, this is not an algebra class. This is not a math class. This is just learning a method, learning analysis methods. So if you find yourself slogging through lots of algebra for this class, you're doing it wrong. Unless you really enjoy it, then go for it. So all of this has been posted online. In fact, there'll be another announcement, I think, on Monday that I have it auto set to just kind of remind you of this. MATLAB is completely free. If you're a Texas A&M student, which you are, you can just log in with your net ID. You can download it. It works on Mac, Windows. I think they got one on Linux, but I'm not positive on that. There's an online MATLAB Live, if you will, just like there's Multisim Live. There's an online version. There's ones for your tablet. There's ones for your phone. It it works quite well. That I use the one on my iPad all the time. So, and you can solve these equations. All right, so I'm now rambled on pretty much this whole time. Anybody have any questions at all? Okay. All right. This is. I'll probably we'll have the next recitation. Technically, we have one next week. I am possibly looking at might be out of town next Friday, so I will make an announcement as to when that recitation would physically take place. It just like this one, it is recorded. It will probably end up being on Wednesday. I'm thinking because I'm also going to be out on Thursday, at least at the moment. So because of that, I'll probably reduce something like Wednesday afternoon. So I'll make an announcement. If you want to come, great. Again, it's one of the things I'm going to go through homework problems that people ask about and and post it. Um, again, this is a totally optional thing. In fact, it's the first time I've ever done these for this class. So all right. So any last chance for any questions, comments, concerns, anything?
The node voltage analysis for when you were solving for node V2, why was the term V2 minus V3 instead of V3 minus V2 over the resistance?
Okay, that's me. Let me put that back up here. So basically on this particular problem here, why was it V2 minus V3? This right here?
Yes, and like instead of being V3 minus V2, I guess like just the sign.
Yeah, that's a good question. Okay, so we're doing analysis on this node, right? Right here on this V2.
Yes.
So everything starts at V2. So we're looking for the current that's leaving through the 10 ohm resistor. So V2 minus 0, basically. So V2 over 10, so we got that, right?
Mm-hmm.
And then we got the current that's going to go from here to here. So V2 to V1. So this one here is the current's going here to here. So that would be V2 minus V1 over 5. And then the next one, the one you're asking about, is the current that's going from here to V3. So it's going to be V2 minus V3. Like we're looking specifically for this current, whatever it is, going from positive to negative, from the positive terminal this way to the negative terminal this way. And we're doing that only as we're staring at this particular terminal. It's going to change when we get to another node. So that's why the like the nodal analysis method um, has you do. Let's see, where is it? You do this step here where you assign element voltages. I don't do this step. I think this step confuses people. It confuses me. So I just stay focused on the terminal that I'm on, V2. So V2 is always positive. If that's why I do leaving currents, no matter what, because it's the current that's going from here to here. Um, now, once we compute the values, I mean, the real current, the actual current going through that device, depending on how you're looking at it, might be flipped. It might be negative, and that's fine. But I'm looking for what is the current going from V2 to V3 through the 20 ohm resistor. So that's why it's positive V2 minus V3.
Okay. And then my next question, I guess like just to clarify, is V2 specifically referring to like the node that's like 2 dots to the left of the 5
Yeah,
ohm
yeah,
resistor?
this is all V2.
Okay. And then
And so again, it's not about the dots, it's about the electrical connection. So all of
mhm,
this is V2. This
okay.
this is V2, that's V2, that's V2, that's V2. All of this area is V2.
Okay. Thank you.
Hmm. And again, the reference node was down here. And then the reference node for all these circuits are typically going to be given. So anybody else have any last minute questions? Okay. I will send out an announcement later on next week's recitation. The next thing we're going to do in class is the mesh current analysis, which is what we'll be covering live in class on Monday. And then next Wednesday, we'll be covering what's called equivalent circuits. And then we'll be starting to wrap up this DC analysis section. This class obviously is moving very fast because 1 week from this upcoming Wednesday, so 2 weeks from this last Wednesday, we will be having a test. So it's going to be moving pretty quick. So the exam review will be 1 week from this upcoming Wednesday, and I'll be doing kind of basically review of the week, the week of the test. So, all right. If there's nothing else, we are done for today. Right. Have a good one, everybody.